So, in the first lecture, I told you about how Einstein reached this special theory of relativity. The driving things were the electrodynamics experiments and the so called unsuccessful attempts to find velocity of earth through ether. So, two postulates I wrote last time. One is principle of relativity, I will talk on that in more detail, and the second was that speed of light is same in all inertial frames. Speed of light in vacuum, it's same in all inertial frames independent of whether source is moving or not moving or who is observing which inertial frame, it is constant. So, these two are the postulates of special theory of relativity. Now, this constancy of speed independent of frame, that comes from a famous experiment which is known as Michelson Morley Experiment. So, Michelson was the senior person and who measured speed of light also using his own design of experiment and did many other things, and Morley joined him to further improve the sensitivity accuracy of the experiment, and this very famous experiment is perhaps the one Einstein is referring to, that unsuccessful attempt and all that. So, let me go little bit into the history of this, or history of light itself. So, as you all know, Newton has done a lot of work on light. He had done lots of experiments using sunlight through a window, small hole in a dark room, and prisms and everything. On colors he has done a lot of work, experimental work. So, all these things are listed in his book Optics, right, Optics by Isaac Newton. A detailed description of all those experiments and the results are given here, and he has tried to explain all those results by taking light to be particles on which forces act, and then the particles accelerate, particles move in straight lines with constant velocity if forces do not act, and all those things like that. Then you also know that contemporary was Christian Huygens, who looked on these experiments in a very different way, and he proposed that light should be a wave. And these things went on. There was no exclusive experiment which can decide that it is wave or it is particle till say the beginning of 19th century, when Thomas Young came up with a double slit experiment and showed the interference of light. So, the interference is some kind of a signature of wave nature, and there, and together with many other experiments, speed of light in water is less than speed of light in vacuum, and many other experiments by Fraunhofer, Fresnel on diffraction. So, those things combined, 19th century beginning 1801 to 1805, let us say, it was established that light is a wave. But then wave needs a medium. That was the understanding. What is wave? Sound wave, for example. So, essentially sound is nothing other than the vibrations of air molecules in a particular fashion. So, when sound propagates, we say that okay, this part of air is compressed or rarefied, and then it exerts force on the other neighboring part, and there you have compression and rarefaction, and that is how the wave propagates. So, the understanding was that there must be some kind of a medium in which this light wave propagates. Then comes Maxwell and experiments on electricity and magnetism, and two things. One is that once you do the experiments, find epsilon naught, find mu naught from the experiments, and then put the values, and you see that this 1 by square root epsilon naught mu naught turns out to be very close to 3 into 10 to the power 8 meter per second from purely experiments on electricity and magnetism. You do an electricity magnetism experiment, get the value of epsilon naught, get the value of mu naught, and then calculate this, and it turns out to be this, which is very close to speed of light, and this establishes that there is some close relation between this light and this electricity and this magnetism. And then comes Maxwell, who writes the entire theory of electric field, magnetic field, charges, currents, and all those, and those Maxwell's equations I am not writing the equations, that will be in the course on electrodynamics, but these equations tell that one can have electromagnetic wave electric field and magnetic field propagating like a wave, and that wave will have a speed which is once again this much. So all this connected tells that okay, light is an electromagnetic wave and its speed should be this much. But if the speed is this much, with respect to which frame? So when I say speed of sound is 332 meter per second, with respect to what? With respect to air in which this sound is propagating. Is the air which is carrying that sound wave, and the velocity, the speed of sound is 332 meter per second at 0 degree Celsius in a frame in which that air is stationary. In this room, if air is stationary and I am speaking, yes, the sound is going at that particular speed. Of course, here temperature is not 0 degree Celsius, so it will not be 332, it could be 345 meter per second or so. But with respect to what? With respect to this stationary air. But if you have wind, then in the direction of wind, speed will be more than this, and opposite to the direction of wind, the speed of sound will be less. In the frame of that air, the speed is given. So if the speed is given, the numerical values is given, it must be with respect to something. And what something? Very naturally, the medium which carries this light, the vibrations of medium portions, they are taking this light wave ahead, and it is that medium which should be taken as the frame with respect to which this speed is measured. So that is how that idea of ether came in, that there should be a medium, and people named that medium as ether, and then the search was on to locate that ether, and it was assumed that that will be absolute rest, because that is the frame, in which light has this speed. So that should be the frame in which all Maxwell's equations should be correct, and if I go to some other frame, Maxwell equations should not be correct strictly. So these were the dilemmas, these were the questions, people were wondering on these, and in that scenario, Michelson came up with an excellent, fantastic idea how to measure the speed of Earth in that so-called ether in which Earth is moving, and that is this Michelson Morley experiment. But before that, let me show you an interference pattern to give you some idea what is that interference, how does it look like, and how it is related to when I will say this Michelson Morley experiment and fringes and this and that. So, you will connect it better if I show you some kind of an interference pattern here. So, essentially interference means at the same place you have two waves coming in, and these two waves which are coming in and superposing at that place, they have some kind of a phase difference. And because of that phase difference, when they superpose, you can have a very large intensity or a very small intensity. So, when the waves combine to give you a large intensity, you say it is constructive interference, and when the waves combine to give you a low intensity, you call it a destructive interference. So, I will just show you an apparatus in which an interference fringe will be formed. You will see the fringe. What do I mean by fringe and bright fringe and dark fringe and all those things. So, let me show you the apparatus. So, it is a very simple apparatus. Here is a laser torch. We are giving some power to it, and the laser is already on. You can see it here on my hand. You have spot, and the beam is going like this. So, the beam is going this way, and then it is falling on a plane mirror. You can see the mirror, and you can see a green spot somewhere here. You can see a green spot somewhere there. So, this laser beam is falling on that mirror, and from there it is reflecting, and then it is reflecting back and going to a wall. So, this beam after reflection is going to a wall, and there you see a spot. So, very simple thing. If you have a mirror, if you have a light beam, the beam will be reflected from that mirror and will fall somewhere. But there is something beautiful about it. Once I dim the light of this room, you will see that it is not just a spot, there is a lot of structure in it. So, let us dim the light and refocus on that spot on the wall. You can see the variation of intensity of light. You have circles, green circles and then dark circles alternately. These are called fringes. So, how come you are getting all these dark and bright circles? We had shown you it is a simple reflection from a mirror, and the spot falls on a particular point on the wall. But when I dim the light, you see it is not just one spot, it is a pattern of bright and dark fringes. So, the light is reflected from the front surface of this mirror glass and also from the back surface of the mirror glass, and these two waves together fall on the wall. So, at different points of the wall, if you see, the phase which comes from the front surface and the phase which comes from the back surface, they are different. They are taking different times, and therefore, at some places you have constructive interference, at some places you have destructive interference, and you see all these patterns. And if I shift this mirror little bit, rotate this mirror little bit, you just see where it is dark, a bright may come there. This whole pattern can shift. That is what I want to show you. So, now I am working on the mirror. Look at this fringe pattern now, and now I am just slightly rotating, and you see what is happening. Can you see the fringe shift? Fringes are shifting, right? The positions are changing. The position of the bright, which is now any bright, you focus on any bright ring, and then see what happens as I rotate this mirror little bit. See what is happening. The fringes are shifting. So, that shift I want you to focus on. If I somehow do something to the mirror, the fringes are shifting. So, now let me come to Michelson Morley experiment. First I will describe the apparatus in a schematic form, and then I will connect it to how this apparatus can be used to measure the speed of earth in ether, if at all it is a relevant word. So, the system is that a light beam, a narrow light beam is sent on a semi transparent glass plate. So, when it falls here on the first surface, part of it is reflected. So, part of it is reflected, goes up 90 degrees at 90 degrees, and the other part goes through this plate and comes out. So, one part is reflected and one part is transmitted. So, let me use this other color here. So, this part goes here, this is the transmitted part and this was the reflected part. Now, you have mirrors, you have two mirrors, one mirror on this line, one mirror here perpendicular to this beam, one mirror, and let me call it M1, and other mirror is somewhere here perpendicular to this beam, this is M2. Now, after falling on the mirror, it will reflect, and this is reflected from here, and that reflected beam that reaches here, part of it at this surface is reflected this way, and the other part goes through this plate and comes out. We are not concerned about that. Similarly, the light which is going on this falling on this mirror M2, that also gets reflected and that comes here, and then it reaches this glass plate, and once again a part of it is reflected which goes this way, which is not relevant for us, and the other part comes here, goes through this plate and comes out. Okay, so let me repeat. I have a beam, then beam splits at this glass plate which is at 45 degrees to the beam, and part of it is going in this direction, part of it is going in that direction. Then you have mirrors perpendicular to the beams, these mirrors reflect the beam, and then again they come to the glass plate, part of it is reflected, part of it is refracted and transmitted, but the part which is going in this direction, in this one direction, that is relevant, and this is captured in a telescope. So, you have a telescope and this beam is taken here. So, there is a phase relationship. This same beam is split here and here. So, they start with the same phase. You have some changes because of the thickness of the plate and reflection, all those things are details which I am not going into. Assume that it is a very, very thin plate and so on. In fact, in the actual apparatus you have yet another glass plate to compensate this thickness in the path and so on, but those things are for details. The essential theory, if you understand, is that here the two parts are split from the same beam, therefore they have the same phase relationship. But then they are travelling this much of distance, it will take some time. This one is travelling this much of distance, it will take some time, and these time may be different. And if these two times are different, then the two beams which are entering the telescope, they will have a definite phase difference, and then depending on that phase difference you will have intensity. And it is not just one ray. Just now you saw we have a laser beam falling on the mirror. Of course, I am using the reflection from the back surface and the front surface. Here that is not the case, it is only that one reflection which is being used. But once you have the beam, not a single ray, you will have at different places in this telescope, in the view of telescope, the beam which is reaching here, it's a slightly different path the one which I have shown here, it is reaches here, but beam is also reaching here, slightly different path. So the phase difference here will be different, phase difference here will be different, phase difference here will be different, here it will be different, and that is why in this view at some places you will have bright fringes, at some places you will have dark fringes. So you find a fringe pattern in this telescope. So you may have, if everything is perfect, then you will get the circular fringes as you saw on the wall, but if it is slight angle, not perfectly perpendicular, generally we get straight fringes. So in this telescope you will have bright fringe, then you will have dark fringe, then you will have bright fringe, and then you will have dark fringe, again you will have bright fringe, then dark fringe, and so on. So this kind of pattern you can see in the telescope. So this is the basic arrangement. In the telescope there is cross wire, so you exactly know at the cross wire what is it. If this is cross wire, let us say if this is cross wire, then you know that at the cross wire you have the center of the bright fringe and blah blah blah. So this is the basic apparatus. Now comes the theory of it, the physics of it, why Michelson designed this kind of apparatus. So first let us talk of speed of light, because I am interested in time, how much time this beam takes and how much time this beam takes. The difference in those two times, that will decide the phase difference. So how much is time taken by the light going from here to here and coming back, then here going from here to here and coming back. After this time is same, and I assume that thickness is small and other things. Okay. So what is the speed of light here? Speed of light is c, but speed of light is c with respect to the ether frame. This is earth frame. Is it ether frame? Same as ether frame? Not necessarily. So there was a notion that time that since earth is going around sun, possibly the sun will be at rest and earth will be moving, and sun will be at rest with respect to that ether frame. So if you have sun here, let us say you have sun here, and if the earth is going in this orbit, if the earth is going on this orbit, and supposing that okay, sun is at rest in ether frame, then what happens on the earth? Since earth is moving in the sun frame, earth is moving this way, and the speed is about 30 kilometers per second. If you know the radius, you can, and 365 it has to make one full round, so you can calculate the speed. That speed is something like 30 kilometers per second. So if sun is at rest in the ether, so your ether is here at rest, and in ether this earth is moving at this speed v in this direction. So as seen on the earth, what is ether doing? On the earth if you are sitting, and in that earth frame if you are looking at, then the ether is going in the backward direction. So that means if this is earth, and here is our whole apparatus, then ether is going this way. Ether is going this way with velocity v. So there is a wind of ether, and if there is a wind, ether wind, then speed of light will be different in different directions. Only in the ether frame in which the light wave is moving, one can say that in all directions the speed is same. But if I am in some other frame, and in our frame ether is moving and speed of light is same in all directions in the ether frame, then in my frame it will depend on the directions. So in our experiment, in this Michelson Morley experiment, light goes from G to M1 back to G, and then comes here. Light goes from G to M2 and then M2 to G and then it goes here. Any calculations on the fringe formation, if we have to make, we have to find the time difference between this path and this path, and for that we need speed of light in direction gm1 and speed of light in direction m1g, speed of light in the direction gm2 and speed of light in the direction m2g, and all these will be different, and depending on how much is the wind speed and in which direction is the wind speed, wind velocity, that will decide all these four different time intervals and hence the fringe formation. There is yet another point. We say that on the earth there is a wind, but then my laboratory, my apparatus can be somewhere on the globe, it has to be somewhere on the globe, and depending on where this laboratory is on the globe, the direction of this ether is different. At one position the same direction is vertical, and at some other position the same direction can be horizontal, because we have a globe. So suppose you have a direction like this, suppose you have a globe here and the ether wind is like this. So here it is vertical, here it is horizontal. So depending on the location of the laboratory, and the earth is moving, okay, so location is not fixed. I am here, after some time I am there, after some time I am there, and so on. Earth is rotating, earth is going around the sun, so all those things are to be taken into account. And finally we need the time difference, and which will make these fringes. So in the next class I will be assuming that the situation is so favorable to us that this ether wind is parallel to one of these two arms, say this arm. So this ether wind is going this way. So we will just assume that ether wind is parallel to one arm, and then we will make the calculation how much should be the path difference, phase difference here, and then we will talk about the genius of Michelson. You get fringes, fine. So whatever be the wind velocity or whatever is the time difference, etc., you will get the fringe pattern. So from this fringe pattern, how to deduce that ether velocity v, that is the genius of Michelson, and we will talk those things and do some calculations in the next lecture.